Alright, so today we're going to look at solving inequalities where we only need to perform one step in order to solve it. The nice thing with inequalities is really the process is the same as equations. So in order to solve them, we're going to be performing opposite operations on both sides of the inequality symbol. And that's just like we were doing with equations. Now there are a few differences. One of the big differences is when we are verifying, we need to verify two things. So with equations it was just one, but for inequalities we need to verify the boundary point, which is basically what we've done already. But we also need to verify the inequality symbol, and that will become very important, and I'll show you why in a couple of examples here. So let's just look at something nice and simple. I got x plus 5 is less than 9. So my opposite operation would be to subtract 5 from both sides, and that leaves me with x is less than, and 9 minus 5 is 4. So my statement says x should be less than 4. Okay, so what this statement is saying is that if I pick any number that is smaller than 4, it should make this original inequality true. And that's my goal, is to find all of the possible solutions. Okay, so the first thing I want to do is I want to verify that this number 4 is actually the correct boundary point. So the way I verify the boundary point is I'm going to verify as if it was an equation. Okay, so I'm going to pick left side, right side, and I'm going to pretend that these two things were equal to one another. Because if they were equal to one another and I had x plus 5 on the left and I had 9 on the right, I'm asking if I instead put in 5 for x, or sorry, 4 for x, will I actually get the correct value? So I put in 4 for x, and then I add the 5. 4 plus 5 is 9. So if this was an equation, that would mean that 4 is the solution. Okay, but this is not an equation, this is an inequality. And we've said that all the numbers that are smaller than 4 should make this original inequality true. So I need this to be a true statement when I say it out loud. Okay, so the second thing I need to check now is I need to check the inequality. So when I'm checking the inequality, I have said that x should be less than 4. So what I'm going to do is I'm just going to pick something that is in fact smaller than 4, that is less than 4. My personal favorite, if you can, pick 0. So 0 is smaller than 4, right? So I'm going to try x being 0. So if I go back, my original inequality said x plus 5 should be less than 9. And I said any number that's smaller than 4 should work. So I'm going to try this value of 0. Let's put in 0. So 0 plus 5 should still be less than 9. And 0 plus 5 is 5. And so you ask yourself, is it true that 5 is less than 9? This is a true statement. And so since that is a true statement, it means that x must be those numbers less than 4. I know it has to be 4 because we proved that the boundary point was 4. Okay? Okay, so that was nice and simple. Let's look at another one. So this one says that 3 times x should be greater than or equal to negative 27. So this one is fine if it equals negative 27. Okay, but we got to find all the things that will make this whole statement true. Okay, so our opposite operation is going to be dividing both sides by 3 because x was being multiplied by 3. So this gives us a statement that says x should be all the numbers that are greater than or equal to negative 9. Okay? All right, well, the first thing I need to do is I need to test that boundary point. I need to make sure that 9 actually is that correct boundary point. Okay? So I'm going to check, I'm going to do my left side and my right side and pretend that this is an equation. Okay, so if I started with 3x and negative 27, if I substitute in negative 9 for x, I get 3 times negative 9, and 3 times negative 9 is negative 27. So we've done a good job. We have the correct boundary point. Okay, so now that I've done the boundary point, I need to check that inequality. Okay, so when I'm checking the inequality, I've said any number that is bigger than or equal to -9 should work. Okay, now I need you to be careful here. Do not pick -9. I don't want to pick -9 because I've already shown that -9 works. I already know that it works. I already know that it could be equal to -9 because in this case it can be equal to the boundary point. I have to make sure that I'm in fact looking for all of the numbers that are bigger than -9. Okay, so when I'm checking the inequality and I need to pick something that is bigger than or equal to -9, I'm really looking for something that is bigger than -9. Okay, so in this case I could pick 0, but I'll try something different just so that you don't think that 0 is the only thing I could pick. Why don't I say try x is -5. -5 is bigger than -9, so this should work. All right, the original inequality was 3x should be greater than or equal to -27. So if I change x to that value that we gave it, -5, okay, when I put in -5, I have 3 times -5 should be bigger than -27. Well, 3 times -5 is -15, and -15 is bigger than -27. This statement down here is true. So because this is a true statement, right, when we say it out loud, it makes sense. That means that the inequality symbol is facing the right way, which means our alligator is eating the bigger quantity, right? So we've verified that inequality, okay? All right, let's do another one here. I got 2x is less than 10, okay? Or sorry, -2x is less than 10. All right, so my first thing to do would be to divide both sides by -2, and this leaves me with x is less than -5. Okay, so just like we've done before, I'm going to check the boundary, and then I'm going to check the inequality. Okay, so for the boundary point, if this was an equation, I started with, I had -2x, and on the right hand side we had 10, so that's -2 times -5, and then I have -10, or sorry, +10, because negative times negative is positive, so I get +10 on both sides. Okay, and some of you are probably thinking, oh, this works every time. What's the point? Why am I doing this? And this is actually our first one where things might not work out for us. Okay, so I'm going to check that inequality. I have this statement saying that x should be anything that is less than -5. Okay, so something that's less than -5, I'm going to pick something easy. I'm going to say -10. Okay, so my original inequality was -2x should be less than 10. If I put in a -10 for x, to -2 times -10, and that gives us +20 is less than 10. And that is false. It is not true that +20 is less than 10. This is bad. Because this is false, it means that this inequality is facing the wrong side, right? This statement would be true if 20 was bigger than 10. So that means my inequality symbol is facing the wrong way, which means this here is actually not the solution. My solution should be x is greater than -5, because my inequality symbol was proved to be false. The boundary point was fine. So if all you do is check the boundary point, you will not find these mistakes. Okay? Now, we didn't really do anything wrong, right? It doesn't seem like we made a mistake. We solved everything like we did normally. Okay? Well, so this is what's going to happen now. When I divide by this -2, okay, when I divide both sides by a negative, and I get this -5, when I divide both sides by a negative, my inequality sign has to flip sides. Okay? The inequality sign has to flip sides. Okay? Here's a very simple example as to why it needs to flip sides. I'm going to solve this a different way. Okay? What if, like when we were doing equations, I said that we could move a variable from one side to the other. So what if I got rid of this negative 2x by adding 2x on both sides? Okay, these guys here would cancel, and I'd be left with 0 is less than 10 plus 2x. Okay, all right, now I would subtract 10 from both sides, and that leaves me with negative 10 is less than 2x. Okay, then I'm going to divide both sides by 2, and this gives me the inequality of negative 5 is less than x. And that's exactly what this says here. They say the same thing. They're written differently. The first one here says that x is bigger than negative 5, and this one says that negative 5 is smaller than x. But they're really saying the same thing. And because they're saying the same thing, they are the same inequality. If you think about it, the alligator is eating the bigger quantity in both, and in both, that bigger quantity is x. Okay, so the other thing to consider is if you were to just think of your number line, if you had something like negative 2, negative 2 is smaller than 3. But if you were to multiply both of those numbers by negative 1, well, now I would have negative 2 times negative 1 is positive 2, and positive 3 times negative 1 is negative 3. Now, the 2 has become the bigger quantity than the negative 3. So when you multiply by negative, you push something to its opposite side of the number line. So what was bigger will now become smaller. Okay? All right, let's do another one here. So we said that worked when we multiplied, or when we divided both sides by a negative. The same thing is going to happen when I multiply both sides by a negative. Okay, so if I'm going to multiply both sides by negative 3 here as my opposite operation, I get x is, and I need to now flip my inequality sign. So I need to flip my symbol so that instead of being a less than or equal to, it now becomes a greater than or equal to. And 5 times negative 3 is negative 15. Okay, so the key is when you are multiplying or dividing both sides by a negative, you need to make sure you are flipping your inequality. Okay, so let's check that boundary point, left side, right side. Okay, so I had x over negative 3, and on the other side I had 5. So I'm going to put in negative 15. Okay, and I'll just do it beside, otherwise I'm going to run out of space here. So negative 15, okay, over top of negative 3. Negative divided by negative is positive, and 15 divided by 3 is 5. So we have the same thing. That means 15 is the correct boundary point. Okay. Now, we flipped the inequality, so let's make sure that we actually were supposed to. Okay? Or maybe you forgot to flip it, and this will tell you whether or not you should have. Okay? So we said that x should be bigger than or equal to negative 15. Again, I'm not going to pick negative 15 because I already took care of that scenario there. Okay? So I need to pick something bigger than negative 15. I'm also going to give you a hint. If your original inequality contains a fraction, I would pick something that is a multiple of the denominator. So in this case, my denominator is a negative 3. I'm going to pick something that is divisible by 3. Okay? So something that's bigger than negative 15, but that's also divisible by 3. Because when I do that, I won't have a fraction left over. So I'm going to try, let's say x is equal to negative 6. Okay, negative 6 is bigger than negative 15, and I can also take 6 and divide it by 3. That'll work out really well. Okay, all right, so let's try that. We'll put in negative 6 divided by negative 3, and that should be less than or equal to 5. Negative 6 divided by negative 3 is going to be positive 2, and positive 2, it is true that positive 2 is less than 5. So that is true, meaning our inequality is eating the correct side. It means that x is in fact bigger
than that negative 15. So this is our solution here, and that will give us all the values that satisfy that original inequality, which was x over negative 3 should be less than or equal to 5. So as long as you pick any number that is bigger than or equal to negative 15, you will get a true statement. Okay, so I'm going to go back to our first slide where we talked about how inequalities were the same and then how they were different from equations. So they were different because we had to verify the boundary point and the inequality symbol. But the other thing that was different was when we multiply or divide both sides of the inequality, by a negative, the inequality symbol flips. And I ran out of space there. Okay, so inequalities, we solve them the exact same way as we would equations. We're still performing opposite operations on both sides, but what you need to do a little bit differently, you have to check two things when you verify to make sure that you have the right answer, and you also have to make sure you're watching out for those negatives. So anytime you multiply or divide both sides of the inequality by a negative, the inequality symbol flips. Okay, when we looked at this first example, I subtracted 5 on both sides. That didn't have any impact. I didn't need to flip the inequality symbol. Okay, subtracting on both sides is fine. That doesn't do anything. It's multiplication and division. In example number 2, I had a negative symbol, but that didn't impact anything because I didn't divide both sides by something negative. Okay, so if you multiply or divide both sides by something negative, make sure you flip your inequality symbol. All right, guys, have a good week.